Okay, this problem says a mass m naught is attached to a spring and hung vertically. The mass is raised a short distance in the vertical direction and released. It oscillates with a frequency f naught. If the mass is replaced with a mass 9 times as large and the experiment repeated, what would be the frequency of oscillation? Okay. So this is really just knowing the formula. So the period, okay, well, like you guys did in lab, you set this in oscillation. It will oscillate back and forth. Okay. And the period of oscillation is given by this formula. Okay. And the frequency of oscillation is inverse of the period. Okay. So what you have is, this is the initial period with mass m naught, and then you want the frequency. So f naught is 1 over 2 pi. So you see, as you increase the mass, the frequency rate decreases. Okay. So f naught is 1 over 2 pi k over m naught, and f is 1 over 2 pi k over 9 m naught. Okay, you're increasing the mass by 9 times. Okay, so as you increase the mass, so f, let's calculate f naught over f is 1 over 2 pi So you can see that everything cancels. All you're left with is root 1 over 9, which is 1 over 3, and that comes to the top, that becomes 3. So when you increase the mass by a factor of 9, the frequency decreased by a factor of 3. Okay? The original frequency was 3 times greater. Lighter the mass, the faster it will oscillate. Okay? This problem says a 0.5 kg mass suspended from a spring oscillates with a period of 1.5 seconds. How much mass must be added to the object to change its period to 2 seconds? Okay. So the period is given by 2 pi m over k. All right, so T1 equal to 2 pi. This is the period with that mass. And then T2 is the period with m1 plus delta m divided by k. Okay, so then you added some mass. Yeah. The period went from 1.5 seconds to 2 seconds. Okay. M1 was 0.5 kgs. All right, so let's just take the ratio of the two. If you take the ratio of the two, all the stuff cancels and you don't have to find that. Okay. So T1 over T2 we know this, we know this, we know that, so this is the only unknown. And you can calculate that. All right, T1 is 1.5 seconds, T2 is 2 seconds, M1 is 0.5 kgs, 0.5 plus delta M. Okay, so we'll square both sides. 1.5 squared divided by 4. Okay. Okay, so you almost have to double the mass. You increase the mass by 0.39 kgs and the period will go from 1.5 to 2 seconds. Yeah. Okay, this problem says a type of BB gun uses a spring-driven plunger to blow the BB from its barrel. Calculate the force constant of the plunger spring if you must compress 0.15 meters to drive the 0.05 kg plunger to a speed of 20 meters per second. And then, okay, so let's say here's the BB gun. I'll draw the plunger like as if it was a bullet. Okay, so this is the compressed position. And then the bullet is fired and it comes out at 20 meters per second. Okay. So the compression is, this is 0.15 meters. So you compress the spring 1.15 meters, okay? So you can solve this using conservation of energy principles. So this will say this is the initial energy, this is the final energy. In this configuration, all you have is spring potential energy. And in this configuration, all you have is kinetic energy for this guy. Okay, so mechanical energy is conserved here. Okay, so 1/2 kx squared equal to 1/2 mv squared. Okay, so we know the mass of the plunger, which is that. We know the speed at which it comes out, so we know this. We know how much you have compressed the spring, and you can calculate the spring constant. Okay, so that's part A. So you have K equal to mv squared by x squared. M is 0.05 kgs. All right, so this works out too. about 900 newtons per meter. Okay. Do you guys have any sense for this number? What does this number mean? What's that? No, Newton times meter is joules. Okay, so what this number is saying is you need about 900 newtons to stretch the spring 1 meter, and here's a meter. And 900 newtons is roughly the weight of 1.5 times your weight. Okay, so a couple of light one of us should hang on to the spring to stretch it 1 meter. That's what that means. You guys, when you did the experiment in lab, what was your spring constant for that? About 10 Newton per meter. So this is a spring that is 100 times stronger than that. 100 times stiffer than the ones you used in lab. Okay? Now they ask you, what must be the force exerted to compress the spring? Okay. So you compress the spring is pushing in that direction, and this is the applied force. So to compress, the compression force you're applying is increasing gradually as you compress the spring. So this is the maximum applied force, which is equal to the maximum force that the spring exerts. So the maximum applied force is K times, and we are just calculating the magnitude is K times the amplitude of compression. Yeah. And so the maximum applied force is, we just found K, 889 Newton per meter, and the compression is 0.15 meter. – 133 newtons, which is 13 kgs, about 30-pound force. Okay. So here's how you get it. So newtons is mass times gravity. G is 10. This is about 13 kgs. 1 kg is 2.2 pounds. So that about 30 pounds. Yeah. Okay, so you saw that. What kind of motion is this called when you attach a mass to a spring and you make it oscillate? What kind of motion is that? It's called a simple harmonic motion. Okay? You see the period is independent of the amplitude and so on. And we talked about this in class. A uniform circular motion. Uniform circular motion is a circular motion at constant speed. A uniform circular motion is two simple harmonic motions. This a motion along like that and like that. Okay, so this saw uses that idea. So it's converting uniform circular motion into simple harmonic motion of the blade. Okay. So you see when this knob is over there, the saw is at its extreme point and it's at rest. When it's here, right here, that's when the blade is going the fastest. Okay, so when it's here, the blade is going the fastest in this direction. When this knob comes here, the blade is gone there. When the knob is over here, the blade is going fastest in this direction. And when the knob is here, the blade has come to its extreme position and has come to rest. Okay. So anyway, this uniform circular motion is converted to this oscillatory motion in the blade. Okay. So reciprocating motion uses the rotation of a motor to produce linear motion up and down or back and forth. This is a reciprocating saw. If the motor rotates at 60 hertz, okay, it's rotating 60 times a second, and has a radius of 3 centimeters, this is about an inch, a little more than an inch. Estimate the maximum speed of the saw blade as it moves up and down. Well, it should be back and forth, okay? So you guys understand that the maximum speed of this guy is equal to the maximum speed of that. Okay? So let's just calculate the maximum speed of this. V max equal to R omega. Remember, this is relating a linear speed to an angular speed. In this formula, what should be the units of this guy? Whenever linear quantities are related to angular quantities, what should the units be? Very good. Okay, so this needs to be in radians per second. So we'll need to calculate that. Okay? So frequency is 60 hertz, which is 1 over a period. 1 over period is okay, 1/60th of a second. Okay, and omega is 2 pi radians divided by the period, so it's 120 pi radians per second. Okay. 1 over 60, 120 pi radians per second. Okay. So V max is R, which is 3 centimeters, 3 into 10 to the minus 2 meters, times 120 pi radians per second. Okay. So the maximum speed of the blade is 11 meters per second, which is about 25 miles an hour. Okay. Any questions on this? Yep.
So how did you get the equation of V max equals to R times omega, like how did you, is that what's in the notes?
Yeah, it's in the notes.
Oh, it is, okay.
It's from chapter 10. So this problem says, how long does it take a child to complete one swing if her center of gravity is 4 meters below the pivot point? Okay, so this is a simple pendulum problem. We'll treat the child as a tiny mass, so her center of mass, her center of mass is 4 meters below. Okay, so the swing is roughly from the ceiling to the ground. Okay, so that's about 4 meters. And this is one swing. So the period is given by 2 pi length of the pendulum divided by G. Yep. So that's what they're asking. What is the period? So the period is 2 pi, 4 meters, and G is 9.8 meters per second squared. Okay, so on the moon, G is less, it's about 1/6, and the period would be longer. Okay. 4 seconds. All right. So that's what the period works out to. What is the effect on the period of a pendulum if you double its length? Okay. So for a simple pendulum, the period is given by, again, you saw the formula a second ago, 2 pi over Lg. So if you double its length, the period will be square root 2 times the old period. Okay. So the final period will be square root of 2 times the initial period. Did you guys understand that? If you double the length, all you get is a factor of root 2 in front of the, okay? Everybody understand that? What if the effect on the period of the pendulum, what is the effect on the pendulum if you decrease its length by 5%? Okay, so T final is equal to root 2, 0.95 times the initial length divided by G. So T final will be square root of 0.95 times 2 pi, and this is the initial period. So the final period will be and square root of 0.95. Okay, so the period decreases by 2.5%. Okay. So look at this. A car's suspension, if a car has a suspension system with a force constant of 5 times 10 to the 4 Newton per meters. Okay. So essentially, the car's suspension system is 10,000 times stiffer than the spring that you dealt with in your lab. See, about 500 newtons is your weight. Essentially, 1,000 of you would have to sit in the car to compress the suspension by 1 meters. That's what the spring constant means. Okay. So if the car had, it was jacked up, and 1,000 of you sat, it would compress, bring it down a meter. Okay, so that's what that number means. How much energy must the car's shocks remove to dampen an oscillation? So that's what the shocks are dampers. Okay, so you hit a pothole, and you don't want the car shaking forever if you didn't have dampers. Okay, so that's what dampens. Okay. So how much energy must the car shock remove to dampen an oscillation, starting with a maximum displacement of this much? Okay, the energy you have is potential energy, which is 1/2 A times this. Okay, that's how much energy the shock absorbers will have to remove. Okay, and then you decide how large the damping coefficient is based on how fast you want to remove that energy. Yeah. So 1/2, 5 times 10 to the 4 Newton per meter times 0.075 meters squared. So what we'll do is, this is 10 to the minus 2, 7.5 times 10 to the minus 2. The square makes that 10 to the minus 4, will kill that. So this becomes half of 5 is 2.5 times 7.5 squared joules. So that's how much energy you have to remove. (140 joules). Okay, so to get a sense for how much energy this is, so let's say mgh will make you jump. Let's say your mass is 70 kg, which is reasonable. Okay, 70 times g is 10. Okay, times, that's 700. What you want is 0.2 times that, times 0.2 meters. Okay, so if you jump 2/3 of a feet, that's the energy, that's 140 joules. Okay. Or if you jump to the ground from 2/3 of a feet, that's how much energy you'll have when you hit the ground. Okay. That's what that means. Okay, this problem says a diving board with no one on it bounces up and down in a simple harmonic motion with a frequency of 4 hertz. Okay, so here's a diving board, and it oscillates back and forth like that. And this is a sort of given an effective spring constant. Okay, the board has an effective mass of 10 kg, so this board is acting like this simple harmonic oscillator with a mass of 10 kg. Okay, and then a spring constant. What is the frequency of the simple harmonic motion? If a 75 kg diver is on the board. So now you'll put a 75 kg diver on the board, so you're adding that mass there. Okay, and the spring constant is still the same. So what is the new frequency? Okay, the frequency for this system, as you saw, is the frequency is given by 1 over 2 pi and k over m. All right, so F1 is 1 over 2 pi k over 10. F2 is 1 over 2 pi. The spring constant is the same. Now with the diver on the spring board, what is the mass, effective mass now? 85. Okay. All right, so we know this frequency is 4 hertz. Okay. So F2 over F1 is everything else canceled. Okay. So F1 is 4 hertz, so F2 works out to And this makes sense as you make the mass heavier. As you make the mass heavier, the frequency decreases. Okay, this problem says a suspension bridge oscillates with an effective force constant of 10 to the 8 Newton per meter. Okay, you see so that's why this chapter was very important. You're modeling all kinds of systems like this simple harmonic oscillator. Okay, this oscillation was modeled like a simple harmonic oscillator, giving you an effective spring constant and an effective mass. Okay. They're doing the same thing for the bridge. See, they're giving you an effective force constant. Okay, so a suspension bridge oscillates with an effective force constant in that. How much energy is needed to make it oscillate with an amplitude of 0.1 meters? So the amount of energy needed to make that spring oscillate is 1/2 Ka squared. That's the amplitude of oscillation. Okay. So 1/2 10 to the 8 Newton per meter, 0.1 meters squared. So this is 10 to the minus 2. That'll make that 10 to the 6. So 500,000 joules. So when the bridge oscillates with an amplitude of 10 centimeters is about that much, 4 inches. Okay. So it has 500,000 joules. Okay. Now what we're going to do is, we're going to provide the energy like this. If soldiers march across the bridge with a cadence equal to the bridge's natural frequency, okay. You guys have heard of the fact that you can have a battalion march across a bridge and break it. So if you march with a cadence that matches the natural frequency of the bridge, you can pump enough energy in it that it could potentially break. Okay. And you might not cross the bridge. Okay, so if soldiers march across the bridge with a cadence equal to the bridge's natural frequency and impart 10 to the power of 4 joules of energy each second, how long does it take for the bridge's oscillation to go from 0.1 meters to 0.5 meters amplitude? Okay, so they're marching and you want to increase the amplitude from there to there. Okay, well, how much energy do you need to pump in? 1/2 Ka final square minus 1/2 Ka initial square. Okay, so that's how much energy you need to pump in. .5 square minus 0.1 square. Okay, so what this is saying is, if you want to increase the amplitude of oscillation from 0.1 meters to 0.5 meters, you need to pump in 12 million joules of energy. And how are you going to do that? By the soldiers marching on the bridge. Okay. And so what's happening? The ATP energy stored in your bodies is being transferred to the bridge. All right. How long does it take for the bridge to go from there to there? Okay, so how long would it take? And potentially maybe you could compromise the bridge if it's oscillating at that amplitude. So we'll calculate how long it takes for them to, okay? And they impart that much energy every second, okay? So B. The time needed is, you need to impart this much energy and divide it by 10 to the power of 4 joules per second. Okay. So 12 times 10 to the 6 joules divided by 10 to the 4 joules per second. Okay. So this is, that cancels, so 1200 seconds. $20. So if the bridge is long enough where it takes them 20 minutes to march across the bridge, you could potentially compromise the structure. Okay, in this, what we didn't assume was, we assumed that, what we assumed was the bridge was frictionless. There's always dampers, okay? But you could also think that maybe they pumped in more energy per second, and that minus the loss was this much. So this problem would still work, okay? All right, that finishes the problems.